So let's get started. So thank you all for coming along to my talk. My name is Noel Welsh, and I'll be talking about the structure of programming revolutions. So we had the keynote today, which is about post-capitalist society. I want to continue talking about big, weighty, important topics. This is a very serious talk. I don't expect any laughing. And I want to discuss virtue and truth, and in particular, the question that really motivated this talk, which was, is Python a good language? Now this is a kind of it's a difficult question. What do we mean? What do we mean by good? What do we mean to be a good programming language? And one way you can answer this is we can use an ethical framework known as utilitarianism. And what utilitarianism does is it equates morality with economics. And essentially what that means is the rule of the masses. So let's turn it over to you and say, is Python a good language? Put your hand up if you think Python is a good language. Okay, a few hands going up. I see you sort of feel. Put your hand up if you think Python is not a good language. And we have a few hands going up. I think in this case, in mob rule or utilitarianism, to give it its fancy name, we would argue that Python is a good language. We had a few more votes. And we had a lot of people abstaining as well, but it's a problem with democracy. Right. So what I thought when I saw this question was really, from an OO perspective, Python is a good exemplar of object-oriented programming. But from an FP perspective, Python is not a very good language from that perspective. It's not a very good FP language. And this got me thinking some more about the difference between OO and FP. I do a lot of training, and one of the biggest problems we have is when we teach Scala is we're not teaching syntax and things like that, language features. We're teaching a different mindset, a different way of thinking about code, thinking about the FP way of thinking about code versus the OO way of thinking about code, and getting people to make that jump. So really, what it means to be an FP programmer is the main topic I want to just explore in my talk. So hopefully give some insight if you are learning Scala yourself on how to think like an FP programmer, or if you're teaching Scala people, if you're a sort of more senior person in the company, then you often end up teaching people Scala. This might give you some ideas on how to make it easier to get people to transition from OO to FP. But before we get into that good stuff, I want to discuss some other ideas to give some context. So I want to discuss some wild ideas from the 60s. Looking around the audience, I don't think anyone remembers the 60s here, but well, we got one person, yeah. So you were probably down in San Francisco in the summer of love, right? So that when people think the 60s, you probably think of like the summer of love, San Francisco, maybe the Beatles, maybe Woodstock, that sort of thing. But I want to discuss some other kind of crazy ideas. These are ideas coming out of Paris in the 60s. So firstly, in the taxonomy of angels. Right, you've probably given some thought at some point in time to the kind of how you would structure angels into species. And this argument that coming out of Paris was that each angel is a species unto itself, because angels do not have material being, and have been immaterial objects. We can't distinguish them unless they are of different species. So the argument is that every angel is of a unique species. That's an interesting one. I'd like to know how that jives with your thoughts about angels. Another thought on the nature of intellect. By a similar argument, we can say that humans share one intellect. So I don't actually need to give you this talk because you know it already. So the human intellect has no material substance, as we all know, and since there is no material substance, there can only be one intellect, because we cannot distinguish these immaterial things otherwise. So there is only one human intellect. And possibly one of the most interesting ideas on the immovability of the universe. Have you ever laid awake at night wondering if God can move the universe in a straight line? Again, you're all educated people, so I'm sure, as you know, following Aristotle, that a vacuum is impossible. So if God were to move the universe, there would be a vacuum where the universe was, and therefore this would be an impossible thing to do. Okay. At this point, I probably ought to fess up and tell you that when I'm talking about the 60s, I'm talking about the 1260s here, not the 1960s. And so the ideas I've been put up on the board were some of the ideas that came from Thomas Aquinas, St. Thomas Aquinas, who I've learned, he has a different name in probably your native language, you may not know who I'm talking about, and other people known as the Latin Averroists, who were at the University of Paris in the 13th century. And so one thing you could be pretty certain of in the Middle Ages is if you had crazy ideas, you ought to expect the Inquisition, and that is exactly what happened in 1270. The Bishop of Paris wrote these condemnations saying you were not allowed to think some of the ideas I've shown previously, and some additional ideas. Here, just a few selected examples. The soul separated from the body by death cannot suffer from bodily fire. Anyone ever given much thought to that one? God cannot grant immortality and incorruption to a mortal and incorruptible thing. God does not know singulars, individual objects or creatures. And then God does not know things other than himself. Right, so this was one of, I think, 3 condemnations that were made in Paris in the 13th century. And if you want more insight into the crazy thoughts of the Middle Ages, go have a read of them. They're quite interesting. But there is a serious point to all this. And I think what is interesting about these ideas is they're not ideas where we look at when we go that's wrong or that's right. There are a bunch of ideas that to us don't even make sense to be talking about. So let's sort of go back. The immovability of the universe. Now, if you are first in modern physics, sort of post-Einstein physics, we would talk about coordinate systems, relativity, and we'd say that there is no way you could observe the universe moving. There's no frame of reference outside of the universe for which you could observe the universe moving. The universe creates space as it expands. It doesn't make sense to talk about moving the universe within space because the universe is space. So there's no external frame of reference for which you could see if the universe was moving. Right? And similarly, when we talk about the taxonomy of angels, species for us is something that only makes sense when you have DNA and breeding and so on. And if you say that angels are supernatural creatures, then there's, even if whether you believe in angels or not, if you sort of accept that angels were to be supernatural creatures, then there's no reason that they should have any kind of species similar to biological creatures, because if they're supernatural, then they are not constrained by the rules of biology. So talking about species of angels as a concept doesn't even make sense from our modern biology point of view. Right, would anyone disagree with those? No, good. Okay, so we're all modern people here. So, this is kind of an interesting way of looking at these ideas. There's not even, no ideas that are wrong, they just don't make sense to talk about. And to get a feel for what this means, I think we need to turn to some more wild ideas from the 60s. But in this case, I'm talking about the 60s that might be more familiar to some of us. I'm talking about 1962 specifically, and this book, The Structure of Scientific Revolutions, by a guy called Thomas Kuhn. Just a quick show of hands. Who has heard of Thomas Kuhn, or Structure of Scientific Revolutions? Okay, a few hands going up, but not so many. All right. So this was quite a landmark in the philosophy of science. Up until then, people had viewed science as a very kind of deterministic process where knowledge just increased and increased without end, kind of the view that Popper was kind of associated with. And in Thomas Kuhn's view, science was a little bit more complicated than this. And he said that science basically went through 2 main phases. The first main phase, called normal science, that's the good times when you're running around in your lab coats and you're doing experiments, and all of your experiments building on some existing theory and adding new knowledge, and everything's good. That's great. And then there's when things go a little bit awry, and we have what's called a revolution, which seems to be our theme of this conference. And this is where you're producing results that don't really jibe with your existing theories. So we had the example of that at the turn of the 20th century with relativity and quantum physics, where people were discovering results that didn't really coincide with Newtonian physics. Earlier than that, we had Newtonian physics and the Ptolemaic astronomy, which is everything revolves around the sun. And basically, you have this situation where your experimental results just cannot be explained by existing theory, and you need to come up with a new theory. Now, this is not a sudden process, like I sort of illustrated here. It normally takes quite a period of time. But you do have this time when basically a new theory is established. And Thomas Kuhn coined a phrase for this, which is paradigm shift, beloved of managers everywhere these days. So next time you're in a meeting and some senior manager says, we need a complete paradigm shift, you feel happy in your soul that you have a philosopher guiding your company. And one of the things about these paradigm shifts and these different paradigms, again, a technical term here in Thomas Kuhn's writing is they're said to be incommensurate. And what this means is that from one paradigm, you can't really understand people operating in another paradigm. So a paradigm is a way of viewing the world, a sort of a fundamental assumptions you make about the world, and trying to communicate across paradigms is very different. Like we saw with those statements from the Middle Ages. They just don't make sense to us. It doesn't make sense to talk about moving the universe because in our paradigm of physics, there's no reference point outside of the universe. And similarly, from our modern biology, talking about species of angels is a nonsensical thing. So this is this idea of incommensurate. You can't communicate across these paradigms very easily. And I see a similar thing when we look at OO and FP languages. So let's just take a little detour to look at the structure of programming revolutions. Right. So to my mind, there have been three main programming revolutions. The first was the structured programming revolution, which started in the 50s. You might say its landmark statement was, "Go to considered harmful," 1968. Anyone read that? Just out of interest? Okay, more hands than I expected going up. That's cool. And by the 1980s, it dominated the industry. So C and Pascal, Turbo Pascal, and that kind of stuff. So structured programming was basically taking the wild and crazy days of assembler and trying to put some structure onto the control flow. So they gave us for loops and while loops and all this kind of stuff. That was the main innovation there. And the next main paradigm shift, object-oriented programming, started in the 60s. I think 1967 was the first OO language, Simula 67. Reached possibly its landmark in 83, Smalltalk 83, which might have been sort of the only true, although the first true OO system. And by certainly the late 90s, it dominated the industry, C++ and Java, that type of thing. The first internet boom. And the third main paradigm shift, I argue, is functional programming. Now, we might say that FP started in the 50s with Lisp, but I think the ideas were really first articulated in the mid-70s, Scheme over in Boston, MIT, ML in Edinburgh. And here are some of the points along the journey. 1990 was when Haskell was created. 95 was when monads were first introduced to the programming world in Phil Weiler's paper. 2007, applicative functors came along. And one thing to note about this is that these dates are much more recent than we saw for the previous ones, right? I could put free monads on there and sort of 2008, I think. So a lot of this stuff is actually very, very new. It's being developed right now, you could say. And I believe that this functional programming is the revolution that is sweeping our industry right now. And if you look across the industry, everywhere is turning FP. So obviously, Scala, JVM, JavaScript, look at systems programming, Rust there, bringing functional programming concepts into there. Swift on iOS. JavaScript, as usual, has 1,000 ideas springing up. We've got Elm and PureScript, FP languages targeting JavaScript, but also things like Flow and React coming out of Facebook, which are bringing FP ideas into sort of more mainstream JavaScript world. Distributed systems, Erlang's been there for a while, and Pony, a very interesting new language showing that you can put types on actors and doing some very interesting stuff there. So I argue that really FP is the change happening right now. We're living through this paradigm shift in our industry, going from OO to FP. And a natural question to ask from that then is, what is the FP paradigm? What are the basic assumptions an FP programmer makes? How do they view code? And as importantly for a lot of us, if you've come from an OO background, how do you make the change? How do you make that jump across the paradigms from OO to FP? All right. That's what I wanted to look at now, spend most of my time. So I've said that a paradigm are sort of the fundamental assumptions that you make. So we talked about like a little bit about the physics paradigm, relativity and so on, biology. What are the kind of fundamental assumptions we make in programming? And I think for a programmer, these come down to what we think of the kind of basic atomic units of programs they are, and also an aesthetic which guides us when we have many possible design decisions, which ones do we choose? What are the kind of principles that good code holds? And it sort of comes back to talking about Python. Is it a good language? It's good from an OO perspective, but it's not good from an FP perspective. So maybe have a think about these. I'd even like to suggest what you think an OO programmer thinks of code consisting of, or programs consisting of. What are the sort of units or the most important features to think about code? Any suggestions from the crowd? Sorry? Constructors, yeah. Anything else? Yeah, tough crowd here. Okay, objects maybe? They're kind of important to OO programming? Yeah. What else? How do objects interact? Right, yeah, so message passing. And I would say the other main thing is polymorphism. So we have objects. Objects interact by passing messages to each other, and polymorphism means that many different types of objects can handle the same message. I think that's OO is something that is not precisely defined, and you sometimes get into these kind of like biblical scholars tracing through the writings of Alan Kay to discern the true nature of the object-oriented programming. I'd sort of like to avoid that and really just focus on how people talk about OO in practice. And I'd say these are probably the main features. And then how do we decide if like a OO programming is good? What guides us towards good code? Anyone have suggestions there? Maintainability. Right, okay. I mean, are there some sort of principles that you can boil it down to? What does it mean for code to be maintainable? Or design patterns. Okay, yeah, design patterns, cool. Encapsulation, yeah. Anything else? Yeah. All right. So there are a few things. Liskov substitution principle might be something that people have heard of. Single responsibility principles, solid principles, design patterns, encapsulation mentioned, coherence and coupling, these types of things. So there are these kind of principles that can guide us. Now, what I think is interesting about these, and this is a bit of a parenthetical note, but still interesting, is that these descriptions are informal. So what does it mean for code to be well encapsulated or code to have a single responsibility? It's kind of informally defined. And also the model of the way that people think about code is kind of anthropomorphic. When people talk about objects, they talk about it in this area as sort of alive and active entities passing messages to each other, which I think is interesting. And the other thing is that the meaning of programs is often determined at runtime. So it's very much a dynamic model because of polymorphism. What an object does with a message when you pass that message is up to the object. It's not something you necessarily know by statically looking at your code. And this motivates things like the small talk debugging experience where you can jump right into running code and make alterations to the code and immediately get it running again. So it's a very dynamic view of the meaning of programs. When we look at functional programming, I think it's quite a different way of looking at code. So the main thing that you look at doing in functional programming is transforming data. So the main thing, that's just about the only thing you do. So rather than viewing code as made out of objects, sort of active entities talking to one another, it's a transformation from some input to some output. That's what a function basically is. You give an input, you get an output. And if I had to boil down functional programming into the key principles, the kind of key aesthetic that tells you what is good, or the key things we believe in, I would come up with simplicity and static reasoning. And these deserve some more explanation. So let's talk about simplicity first. Many languages claim to be simple. Haskell claims to be simple, Go claims to be simple, but they're very different languages. And simplicity is often something people use as a weapon to say, my code is simple, your code is not. And usually what people mean when they say that type of thing is, my code uses concepts I'm familiar with, and I'm not familiar with the way you've written your code. So if we can have a meaningful discussion about simplicity, we need to have a definition that's reasonably precise and goes beyond just familiarity, and allows us to distinguish between, say, Go and Haskell. So the definition of simplicity I want to use is we have as few concepts as possible and at all scales. So it's this scalability argument which distinguishes Go and Haskell. So Go has few concepts at the low level, but at the high level it's say just write more code, repeat yourself, which is not the approach that Haskell takes, for example. So let's look at how that plays out in Scala, say, and look at both a low level in code and a kind of high level structure in code. So one place we can see this at the low level is in control structures. So in your typical OO language, following structured programming, you probably have for loops, while loops, do while loops, and you have recursion. And in a typical FP language, you have recursion, because recursion, you can do everything you can do with a for loop and a while loop or a do loop. So why introduce additional concepts when you don't have to? So that's one way that this desire to minimize concepts plays out on the small level of code. At the high level, we look at abstraction. So for example, if we have types list, option, future, we say, what can we say about all of these types? What can we say they have in common? And in a typical OO language, the answer is nothing. You don't say anything about them they have in common. And in a language like Scala, you may say they're all monads, for example. And you use some language features to make this work, right? You need high kind of types in there. But it's the main thing here is abstractions allow us to make different things that are the same. So we can say all these different concepts are all monads. And I think in functional programming, there is that kind of bias towards finding abstractions. Functional programmers love abstractions because it allows them to reduce the number of concepts they deal with. Instead of having lists and options and features, you can just say they're just a monad. They have this interface. You can interact with them in this way, which is nice. Okay. Let's look at something else. Let's look at how people understand their programs. So it's something called the substitution model of evaluation in functional programming. I'm going to ask you some questions now, and before we get into those questions, I want to say they're not trick questions, okay? They have an obvious answer, and the obvious answer is the correct one. And also, when I asked these questions in New York, I had a very difficult time answering, which reflects poorly on the US education system. I want you to show me that the European education system is far superior to the US education system. All right. So let's look at this program, 1 + 1. Can anyone tell me what this program evaluates to? Am I hearing that the death of European education? Anyone with an answer? 2. Thank you. Okay. You're absolutely correct. 1 + 1 evaluates to 2. Right? Okay, now I'm going to get a little bit harder now, but I think you guys can do this. What about 1 + 1 plus 1 + 1? Right, okay. We got it. 2 + 2, yeah, you're right. 2 + 2, or 4. Now, the point about this is, in the substitution model of evaluation, when you see an expression, you can substitute in its value and you don't change the meaning of the program. So whenever you see 1 + 1, which is equal to 2, you can substitute in 2. So here we have 1 + 1 plus 1 + 1, And if substitution holds, we know that 1 plus 1 is 2. We can substitute in 2, and we get 2 plus 2. And as you correctly told me, 2 plus 2 is 4. And that is how a functional program thinks about the meaning of their programs. You can substitute in the value of an expression for the expression. Now, substitution is simple using the definition I gave earlier, because we try very hard as functional programs to maintain substitution. One rule for thinking about how the meaning of our programs. And this is why we have things like monads and that, so we can delay effects, so we can maintain substitution. The other thing I believe that I'm not sure the evidence supports is that substitution is easy for people. I hope you all learned this in primary school, though the delay in the answer makes me a little bit worried. We got there in the end. So in theory, and the point I put these really simple, trivial examples up, is to show you that this stuff is very easy. Substitution is no more complicated than doing that primary school level maths. And that is the point. The point is it's trivial. That's why we strive to maintain substitution, because it makes our life really, really easy to work out what our program is doing. You did do better than New York, though. I've got to say that. Go Europe. Okay. Another important point about substitution is that it's compositional. What I mean about compositional, compositional means that the meaning of an expression is determined by the meaning of the sub-expressions and the way that they are combined. The way that they are combined. So we saw that here, right? We had 1 plus 1 plus 1 plus 1 with the 2 sub-expressions we can substitute. We get 2 plus 2, and we can compose that together to get 4. That's compositionality in practice. Fancy word, easy concept. And this is one of the reasons we avoid state in our programs as functional programmers, is because avoiding state allows us to be compositional. When you have state, things don't compose because the order in which you do things matters. So let's have a look at how that plays out in programming. So again, look at the low level, we have expression-oriented programs. So in Java, you might write, well, it's kind of Java-ish Scala, or as we call it, Java without semicolons. You might write this type of thing if you're doing a comparison, make us a kind of an ordering. So we have a mutable variable x, and we're changing the value of x. So this is breaking substitution, because the order in which you do things matters. You can't just substitute in the value of x, whatever it is, 0, I guess. That initial value of x you can't substitute in throughout your program to understand what the meaning of x is. It changes. So what we would do in Scala is we would make if an expression, so it evaluates to a value, and then we can just do this directly. We don't introduce any state into our program, and substitution holds. That's a very small, low-level example. We see that pervasively in functional programming languages. They're sort of expression-oriented, if you like. At the higher level, we have a very, very common pattern, separating, describing, and running computations. Such a lovely, fancy word, but what it basically means is you're splitting your program into two. You have a bit of the program where you tell the computer what you want to do, but you don't actually do anything. And then you have the time when you tell the computer, okay, I've got all my instructions ready, now go and do them. And that's when you have your effects, the things that break substitution. So a kind of typical example of this is something involving a monad. You don't have to necessarily understand all of the code. But the main point here is that we have up top, we're describing what we want the computer to do. We're saying, open a file, read all the lines, print out all the lines, then close the file, and give me the number of lines that you processed. But we're not actually doing that until we go and call run here. And then stuff happens, the file is opened, the file is closed, and so on. The effects happen, and we get an integer out. Okay, so this separation between describing programs and running them is very, very common in functional programming. It's the way that we handle effects without breaking substitution. And you'll see it everywhere. You'll see it in sort of monadic I/O. Like example, we have an image library called Doodle, which has the same setup. You see it in the way people handle random numbers, generating random data, probabilistic programming, so on. A very common pattern. Another difference, in object-oriented programming, types are often seen as busy work, something that you do to make your code run fast. And I think that's the experience a lot of people have had with a language like Java. Part of this is down to the technology, missing type inference and so on makes they're much more of a hassle to use, but I think there's also a cultural factor. If you read the writing of OO people like sort of Uncle Bob and so on, they're very strongly against types culturally. For the FP programmer, and I guess I'm talking about the statically typed FP programmer here, types are something different. Yes, they allow the compiler to warn us when we've done something wrong. Yes, they allow the compiler to optimize our code. That is not their only function. And one of the main functions is to help us to understand our own code and to help us to write our code. And I want to give you some examples now. Okay, so another audience participation time. Again, it's not a trick question. We have here the method foo, not a very good name, but we have some types here. It takes something in of type A and it returns something of that same type. Can anyone tell me what the implementation of foo is? The types constrain the implementation. Yeah, identity function. Yeah, exactly right. So you have to return the input. In fact, there are two possible implementations here. You could throw an exception, or sort of, not terminate, if you like, or you have to return the input. And this you can tell entirely from the types. So the types are constrained implementation such that these are your only possibilities. So here, the types are helping us to understand the code. The name, despite it doesn't matter what the name is, this has to basically be the identity function. And then we can tell that from the types. And the reason being that A is any type. There's nothing you can do with this sort of A. It's not a specific type. There are no methods you can call on it. So basically the only thing you can do is return it or throw an exception. Okay. Now let's look at another example. And here we'll show how we can use the types to guide us in writing a program. So we want to implement the map method on option. This is something we often do in our training courses with beginners, and it's something that they kind of freak out a little bit. But what I want to show you is that it's a very mechanical process for implementing map, and you are very much constrained by the types to guide you towards the correct solution. So if we start here, we've been given the signature for map. This is what map is. Go and implement it. The first step is to say, well, option is an algebraic data type. Algebraic data type you can always process using structural recursion, so you can go and write down this skeleton straight away. Now, the terms algebraic data type and structural recursion may not be familiar to you, but you've probably seen this kind of pattern matching before if you've programmed in Scala, so you can see what we're doing here. So option is a sum or a none, so you have to handle the none case and you have to handle the sum case. That's what we're doing here. So this follows straight away from the definition of option. Right? No thinking required. So now we have two cases. We have none and we have sum. So let's look at the none case first. What can we write on the right-hand side to make this compile? We have to return something of type option B. We don't have anything of type B around. We have a function that will convert something of type A to type B, but we don't have anything of type A that we can pass to that function. So there's only one possible thing we can put in here to make this compile. Anyone tell me what it is? Yes, exactly. Okay. So the types here have guided us to the correct solution. Again, there's no thinking required. This is just a straightforward consequence of the types. Then we get to the next case here. Now we have two possibilities. We could write none, again, that worked. Or we could write, what could we write here? Sum and some FA, yeah, exactly. Okay, and the reasoning, of course, is we have something of type A, we have a function from A to B, this will create something of type B, to create an option of type B, we'll wrap it up in sum. So again, the types guide us towards that implementation. Though we did have to do a tiny amount of thinking there to not just write down none. So we can see that by having the types here, and a very small amount of thinking, we managed to derive the correct implementation of map, which is something that for beginners often seems very, very difficult. But we can see it's actually very easy if you know the reasoning process to get there. And this, of course, is all down to the types. And the kind of logical extension of this is to then use the types to generate this boilerplate code for us. And this is something that Shapeless does in various ways. If you use a JSON library, there's a good chance that your library will generate the serialization and deserialization code for you automatically, quite possibly using Shapeless, its labeled generic feature. And there's similar things for what's called type class derivation for implementing these methods like map and flat map based on the types and doing that all automatically. So that's a great example of how we can do less work by using the types to represent the structure of our code in a way that the compiler and then macros can chew over and do work for us. Right. So to sum up, my argument is that the fundamental paradigm for the functional programmer is based on these two ideas of simplicity and static reasoning. Simplicity meaning as few concepts as possible, and static reasoning being understanding code before you run it, understanding it in terms of its types, understanding it in terms of substitution, and some of the smaller points we saw, sort of subpoints that come from this are the substitution model of evaluation, composition of understanding big things in terms of small things and how they are combined, using types to guide implementation to understand code. And all of this is very precise compared to the OO world, which is kind of an informal definition. Here we can write down like a mathematical definition, if you like. So we can say precisely, does this code maintain substitution or not? You can prove something does or does not, if you're so inclined. So the next thing to then look at is to say, okay, so this is the FP paradigm. How do we go from OO to FP? Because most people have been taught OO programming. If you're experienced programming, you've sort of grown up doing OO programming. So can you go from OO to FP? And views on this differ. So we have Max Planck, a cheery fellow. I imagine if this was what all of his summers were like, he would be kind of upset as well. I'm a bit more optimistic than Max. So I believe that you can go from an OO program to FP program, and I'll hold myself up as an existence proof. I did start off as an OO programmer. And I think one of the ways that we can ease that transition is to look at OO design patterns. So when you look at OO design patterns, what you see there are often a lot of basically FP ideas dressed up in a kind of different terminology. So here are some examples. The chain of responsibility, the command pattern, the strategy pattern. These things are all basically variations on the first class functions, closures, lambdas, whatever you want to call them. So chain of responsibility is essentially when you have, it's essentially function composition. You have an object which is responsible for doing something, and it then passes on its result to the next object in the kind of queue of objects, if you like. And these objects are essentially functions, and you're essentially composing them together. The output from one becomes the input to the other. It's essentially function composition. The command pattern is basically representing a command, if you like, an action as a noun, an object. That's basically as a function in object terms. And the strategy one is doing the same sort of thing. It's a way of doing something, if you like, as an object. So there's all these kind of different ways of where OO people were kind of grasping around, trying to understand the elephant, if you like, of first-class functions, but not quite able to express it in the languages of the time. And you'll see similar things when you look at things like the visitor pattern, which is very similar to a fold, and so on. Now, this will help you to understand how to use some of the sort of FP features, but it's not going to give you this pervasive way of thinking about programming, this different way of thinking about programming that the FP programmer has. So the paradigm is still different. When I was an OO programmer, patterns were normally something you sort of brought out on special occasions, weddings and birthdays or something, not something that you kind of used all throughout your code. So yeah, the paradigm is different, and you do have to change that paradigm, and that is hard. I think well, I hope I've managed to explain to some extent what that paradigm is. Right, so conclusions. Multi-paradigm development doesn't make sense. So it doesn't make sense by definition, but I don't think it makes sense practically either. Like I don't believe object functional code is a reality because you have fundamentally different ways of approaching how you structure your code, how you decompose a problem. So the combination of modular programming and functional programming to me makes a lot of sense. The combination of object-oriented programming and functional programming doesn't. Possibly a controversial statement. I believe OO patterns will help you get to FP concepts, help you to understand how to use language features in an FP world. But they're not going to give you that paradigm, that way of thinking. I hope I've been able to explain that paradigm to some extent, show that it's not so difficult, but like all things, it does take time to internalize. You can't learn instantly, or you have to beat your head against this for a bit before it sinks in. All right, so that's everything I've got to say. Thank you for your attention, and are there any questions? Let's put up the acknowledgements. Well, thanks. Okay. Let's have some questions. Surely someone's got a question. Yeah, do you want
in Scala, you have also the object-oriented part.
Right.
So, but this is less important, I guess.
So if I'm going to kind of expand that out into a question, I would say, how do I reconcile what I said with the fact that Scala has OO features? Is that a reasonable kind of summary of what you're getting at? Yeah, okay. So I think this is very interesting. So if you've read the paper Worst is Better, it makes a suggestion that sometimes it's not the kind of pure expression of an idea that wins out, but it's something that works with where we currently are today. And I think that's an example of what Scala does. Scala, the reason people use Scala is because they can start out using OO ways of programming. They can do the Java without the semicolons, as we jokingly call it, and still they can write that in Scala. Whereas making the jump straight to Haskell or whatever is too much. So Scala works because you can keep on doing things the old way, but that is at some point becomes baggage and it slows you down. So I haven't seen anyone who combines OO and FP in a sort of successful way without there being lots of tension. Okay, that's fine. So yeah, I don't know how much of that is kind of legacy and how much of it is just it's kind of needed to be done. Maybe you can comment on how you. So the issue I always have with O and FP is how do you make the decision of how to break down your code? And I think there's.
It's very simple. I come from the ML world where we use modules a lot.
Mm-hmm.
Haskell, they don't do that. What modules where objects are now? I use objects like I used to use modules.
Right. So so I would definitely agree with using objects as modules. That for me works very well. What doesn't work for me is using things like very deep nested hierarchies of classes. So I would very rarely have an unsealed. I would have if I have a trait, it's either sealed, which is defining an attribute data type, or it's a type class basically. But having like open extension, open classes.
That's definitely a trade-off. It's very powerful. We have that a lot in the compiler. I think I'm not sure how we would do certain things otherwise, except for these deep hierarchies. But it certainly can get into trouble. I absolutely agree with that. It's a seducing thing. And like everything, I think it's sort of a principle of least power. So it's a very powerful way to essentially have inheritance and hierarchies, and use it only if you must, would be my advice.
Mm-hmm. Okay, well, I could agree with that. Thank you. Any other questions? direct them to myself or Martin. Okay, so I guess the only question is it time for lunch? And I guess it is. So thank you all for your attention. Hope you enjoyed the talk.